Okay, welcome to our second class in resistors, and today we look at resistors in parallel and how to simulate such a situation. So let's say we have these resistors in parallel. Have resistor 1, rotate by pressing Ctrl R, resistor 2, and resistor 3. Oh no, I don't like this. So let's move this around so the numbers will be fine. To move, you click on the drag, click on the component of interest. That looks better. We get a voltage source. Rotate. We put a ground for reference. The next we'll join with wires. So one interesting thing about this LT Spice is you can simply click on one end and join the wires to the other end. It will automatically connect the points of interest for you. The next, we select the voltage, the resistance values, or so here we choose 30, just as we had in the first one. Here we choose 20, and here we choose 10. For the voltage value, we choose 20 as before, just to see the main difference between series and parallel resistor connections. The next we will have to do is to simulate again. We use a transient method because of the first problem, and so we want to simulate only for 1 second. That is fine. Let's bring our circuit to view. So we drag, take the whole circuit and bring it to view. Okay, let's reduce this a bit. Fine. So we have more viewing options. Okay, at this point we want to make some measurements. How much voltage cut across this point? 20 volts. How much voltage cross across R2? 20 volts. And how much voltage is dropped across R3? 20 volts. So something is very pronounced here, that voltage across R1 and R2 and R3 is the same. Let's see how this is also affected by current. So as we know, the current flows from negative to positive because flow of electrons is from negative to positive. That's why you have this arrow in this direction and this arrow in this direction, the red arrow and the red arrow in this direction. So when we click here, we'll see that the current through R1 is 2 amps, as you can see. Okay. We have a problem here. Let's see how to get this problem sorted out, because we cannot see all the. Okay, so we have a better view of our screen. Let's make the measurement again. The current through R1 is out of scope. Now, okay, we have to reduce the time of our transient. Okay, let's try again. Transient time, simulate, edit, transient time. I want to measure only for 0.5 seconds and simulate again. Okay, I now have to reduce my transit time and measure currents. Okay, so here I have 2 amp and here I have 1.1 amp and here I have 0.7 amp. So let's change the scale to between -2 to 0. Since the numbers are in negative, but the numbers are actually not negative, they are positive numbers. Okay, so we have the 3 measurements we have here: -2, -1, and 0.8 thereabout. In our calculations, let it be clear that the numbers are not actually minus. So we have 2, 1, and 0.6, and that's what we have here: 2 amp, 1 amp, and 0.6 amp. So that's very important for us to note down with regards to resistors in parallel. Okay, as we can see here, this illustrates that the current across the resistors in parallel is divided across all the resistors, and the sum of the current is now the sum of the current flowing from the voltage source. Another important aspect we have mentioned before is that the voltage across the resistors in parallel are all the same. So in the next section, we will look at voltage dividers and how it affects the choice of resistors and what applications that can be done with.